All right, so now we'll talk about fossil fuel generating plants. So a coal power uh, plant, for instance, how electricity is produced. There are two main kinds, thermal generating stations and combustion turbines. Okay, so for instance, here's a uh, coal power plant. So here's coal. You take coal and uh, you burn the coal in the furnace, which is heating water, and that produces steam. The steam is turning that turbine, which is turning that loop of wire to produce electricity. So that's the whole idea. You, from the heat released, you turn the turbine, that loop of wire, which produced electricity, and the electricity is sent on transmission lines to your home. And then most of that energy is uh, so. Here's the steam, and that steam, the unused portion of the steam, has to be condensed and sent out to the river. A coal power plant is about 33% efficient. So what that means is out of 100 joules of heat released, only 33% is converted to electricity. 66%, 67 joules of the heat is dumped into the river. Okay. So out of every $3, $1 is converted to electricity and $2 are thrown out the window. All right. Uh, so keep that in mind. So thermal generating station uses combustion of fossil fuels, commonly coal, but also oil and natural gas to boil water to make steam, which runs a turbine to a generator to produce electricity. All right, so here's another cartoon picture. You burn a fossil fuel, you boil water to get steam, high temperature steam, which turns that loop of wire, uh, turns a turbine, which turns that loop of wire, and electricity is produced. And then you dump that lower temperature steam. Okay, so that lower temperature steam, and you have to get rid of all that heat. So, so remember, a large power plant is 1 gigawatt, a billion joules per second. So to produce a billion joules per second, you have to dump 2 billion joules of heat per second. So you had to figure out a way to get rid of an enormous amount of heat. Okay, so that in itself is a problem as well. Okay, so you got to figure out how to dump all that heat. So for instance, these are devices to dump heat into the atmosphere. Okay, so these are cooling towers um, used to dump heat into the atmosphere. Okay. All right. So here's a rotor assembly for a steam turbine. So the steam is turning this turbine, which in turn turns that loop of wire. So rotor assembly of a turbine showing the blades. So heat transfer to the environment. So like I said, in a 1 gigawatt, in a power plant producing 1 gigawatt of electricity, you're dumping 2 gigawatts of heat. And the so that's a problem that needs to be solved, and you have to worry about that. So the cooler the temperature of the cold reservoir, higher the efficiency of the heat engine. Okay. By the way, so okay. Uh, so that's an aside. Anyway, so heat dumped by exhaust to the cold reservoir needs to be removed in order to keep the Carnot efficiency high. So you won't need to dump the heat into the environment, but you don't want the temperature of the environment to get too high for various reasons. One of them being your Carnot efficiency goes down. So the way to dump heat is use large bodies of water such as oceans, rivers, and lakes uh, to dump your heat, or you can dump it in the atmosphere using the cooling towers that I just showed you. Okay, so these are the cooling towers you can use to dump in the um, atmosphere. Sometimes, if you have to dump too much heat in the rivers, when the rivers run low, the temperature of the river's water can get high, or that of the lake can get high, and the fish don't like it. So then this is another option. A combustion turbine is similar to a jet engine. So you use a combustion turbine when you're using natural gas. It's more expensive to operate than a coal-powered thermal station, but can be brought online quickly during times of high demand. Now, here's the thing about electricity. You produce exactly how much you're using. So as the demand goes up, you need to bring production online fast, and a combustion turbine is a good one too. It has a fast response time, so it's useful for that. It's more expensive, but the fast response time is necessary. Okay. So a combustion turbine has a compressor to compress air to put it to burn with the fuel. The combustion system is made of fuel injectors. So you compress air, you put in fuel through fuel injectors, and then the combustion produces a high temperature, high pressure gas stream, which turns the turbine, which turns the loop to produce electricity. Okay? So you're using compressed air, injected fuel to produce a high temperature, high pressure gas stream, uh, and expands to the turbine section. The turbine is an intricate array of stationary rotating sections of airfoil blades. As hot combustion gas expands through the turbine, it spins the rotating blade. The rotating blades perform a dual function. They drive the compressor to draw more pressurized air, and they spin a generator to produce electricity. So you are turning that loop of wire to produce electricity. Okay. So here is a combustion turbine in New Mexico. Here's a picture of that again. Combustion turbines, they mostly run on natural gas, and they have fast response time. You can um, start producing electricity at very short notice. Okay. Now here's the current model. Electricity is produced at far off locations, and it needs to be brought to your home. Now it turns out that as electricity is transmitted, you lose some part of your energy, and losses can be as high as 10%. Okay, so you want to minimize these losses, and to minimize these losses, if you transmit them at high voltage, the losses can be minimized. So the losses, the power you're trying to transmit times the resistance of the wire divided by the voltage at which you're trying to transmit. So the higher the voltage you transmit at, the lower the loss. And that's the idea. And of course, you transmit at a high voltage, but in your home you don't want that at high voltage. So you have to use a series of transformers, step down transformers, before you can send that electricity to your house. So here's a step down transformer, for instance. Okay, of course there's many other step down transformers. This is the one close to your house, which I think brings it down from 480 to 240 volts, something like that. All right, that covers the concepts from this chapter.